In this screencast, we're going to talk about random variables. A random variable is a numeric outcome of a random event. So, example, you roll a die, you get a number, 1, 2, 3, 4, 5, or 6. Or you flip a coin 100 times, and X is the number of times the coin comes up heads. It could be any number between 0 and 100. Or you invest in a portfolio of stocks and bonds, and X is the return on investment next year. Or you choose a random order at Amazon.com, and X is the dollar amount of the order. There are two kinds of random variables, discrete and continuous. And mostly in this course, we're going to be talking about one particular continuous random variable, but it's a little important to know about the others. So an example of a discrete random variable is rolling a die. There's 6 things that could happen. A continuous random variable, there's infinitely many things that could happen. In an investment portfolio, the return you get could be any number in some range, like 2.457% or 2.458%. It's not just a finite number of things. And when we talk about random variables, the things we care about are what are the numbers that could come out, what are the outcomes, and what's their probability. We're interested in the average outcome, which is called the expected value, and we use E of X to talk about that. And we're also interested in how variable the outcomes are. Usually we talk about the variance, which is denoted V of X, and it corresponds to the square of the standard deviation. So variance tells you, in a stock portfolio, would tell you how risky, how volatile the investment is. So with discrete random variables, the outcomes and probabilities are often given in a table. So if you roll a die, the things that could happen are 1, 2, 3, 4, 5, or 6, and they all have probability exactly 1/6. Now we're going to save the expected value and variance for discrete random variables for homework, and we won't use them much in this course, but the School of Business does use them for those of you majoring in business. We're going to talk about normal random variables. So this is one example of a continuous random variable, and it's the most important one and the only one we'll talk about in this class, but there are others. So a continuous random variable is described by what's called a density curve, and we'll use this picture as an example. So orders at an online store have mean 400 and standard deviation 50, and we picture the outcomes as being numbers that go from roughly 250 to 550, centered at 400, and a normal distribution has this bell-shaped curve. And when we say that the orders follow this distribution, what we're really saying is that if we made a histogram of the order amounts, it would fit pretty well into a picture that looked like this. And the way to interpret this picture is that if you want to know what's the probability that an order is between $350 and $400, for example, you ask yourself, well, what percentage of all the area under this curve is between 350 and 400? So the classic bell-shaped curve is the normal distribution. And again, this is one example of a particular continuous distribution. There are others where it's also a curve like this with an area under the curve, but it doesn't have that shape. But we're just going to be talking about this one. So a normal distribution can have any mean and any standard deviation, but all normal distributions share some common properties. And the reason normal distributions are so important is because many things that come up naturally follow a normal distribution, and we can use normal distributions to get information even about data sets that are not normal. And we'll see how that plays out later in the course. The kinds of natural phenomena that follow normal distributions are things like how tall people are, or people's IQ. Scores on standardized tests usually follow a normal distribution. If you manufacture things on an assembly line and they're supposed to have certain dimensions, certain specifications, then there'll be some variation. So if it's making wheels that are supposed to be 2 inches in diameter, well, if you measure them accurately, there's going to be a little bit of variation, but it'll follow a normal distribution. And the key that makes everything work is our z-scores. If you have any normal distribution and look at their z-scores, then they follow the what's called the standard normal distribution, the one that has mean 0 and standard deviation 1. And the cool thing about the standard normal distribution is we can know everything we want to know about it. We want to know the probability that z is less than something, z is greater than something. We've got it all. And the Excel function that does this is norm.s.dist of z. And we'll see in class how to use this. So at an online store, the mean sale is 400 with standard deviation 50. What proportion of sales are for less than 460? So that's the shaded region. If we think of all the area under this curve as being 1, what's the area to the left of 460? And the key is to find the z-score that goes with 460. So the z-score that goes with 460 is 460 minus 400 over 50. That's our z-score formula. The x minus the mean over the standard deviation gives us 1.2. And then using Excel, that norm_s_dist function, you put in 1.2, and it also needs you to put in true all the time. It gives you 0.88. And the way to interpret this is that 88% of orders are for less than $460. And if you look at the shaded region, that makes sense. That looks like it could be 88% of the total area. So norm_s_dist and the standard normal distribution is the key. Now using StatKey, we can do this another way, where once we know that the z-score is 1.2, we can tell StatKey to just show us what percentage of the area of the standard normal distribution is below 1.2, and it automatically tells us that it's 0.885. So again, we'll be plugging in the z-score, and then StatKey gives us this 0.885. And we'll see how to do that in class. But you can also just start exploring with StatKey if you want to try to figure it out before class. Another example, at the same store, what percentage of orders are for more than $420? Well, we find the z-score that goes with 420. So 420 minus 400 over 50 is 0.4. And we put that into norm_s_dist, we get 0.66. But remember, norm_s_dist always tells us the percentage less than something. 66% of orders are for less than 420, so we must have 34% for more than 420. And once we know the z-score, once we know that the z-score is 0.4, we can also do this in StatKey and get directly that that the percentage is 0.345 actually. So by putting in 0.4 for the z-score and telling it that we want to see what's to the right, it gives it that number to us directly. Well, what if we want the proportion that are between 380 and 420? Well, now we need to find two z-scores. For 420, the z-score equals 0.4, as we did in the last slide. And for 380, the z-score is negative 0.4. So what we do is we find the norm_s_dist for each of them and subtract to get that 31% of the orders are between 380 and 420. So we do each of them separately and then subtract the two areas, and we'll get 31%. And my advice to you is to always shade in the area corresponding to what you want, that it's useful to help keep you on track. Or if you use StatKey, the picture should help you make sure you're looking at the right area. What if you know the percentage and it's the x you want to know? So for example, at our store, how large does an order have to be in the top 5%? Now, norm_s_dist takes a z and it gives you the proportion. The Excel function norm_s_inverse takes the proportion and gives you the z, and then you can solve for x. So you want the top 5%? Well, if you're looking at the top 5%, there needs to be 95% less than that amount. So you put 0.95 into norm_s_inverse, and you get 1.645. And so then you solve an equation. 1.645, that's the z-score for the x you want, so x minus 400 over 50 equals 1.645. And when you solve this equation for x, you get 482.25. So to be in the top 5%, an order has to be for $482 or more. So to solve problems like this, you use the inverse function, or StatKey, to find the z-score. And then again, once you know the z-score, you can find the x. A z-score formula If we know z, we can find x. If we know x, we can find z. And in StatKey, the way we would do it is we would tell StatKey that we wanted to be in the top 0.05, that we had the right tail is 0.05, and then it would tell us the 1.645. So here's a summary. To find the proportion less than a given x in a normal distribution, find z, take norm s dist, and that's the proportion. To find the proportion greater than x, do the above and subtract from 1, or 100%. To find the proportion between two x's, find the proportion less than each and subtract. Draw a picture. To find the individual with the proportion p less than it, then norm s inverse of p tells you the z-score, and then you solve for solve for x rather in the z-score formula. If you want to know what x has 20% above it, though, remember you need to start with norm s inverse of 0.8. Even more advanced, so at a different store the mean is 400, but to break into the top 5% an order has to be for $515. What's the standard deviation? So now it's the standard deviation that's unknown. But to be in the top 5%, you still need a z-score of 1.645. So you plug that into the z-score formula, but now it's the standard deviation, the denominator here that you're solving for. 1.645 is the 515 that puts you in the top 5%, minus the 400, which is the mean, divided by this unknown number, the standard deviation. And when you solve that equation, you get the standard deviation is 70. So there's four basic kinds of problems we can talk about. Given an x, find a proportion. Given a proportion, find an x. Given a proportion, find the standard deviation. Given a proportion, find the mean. In other words, for any three of the numbers, the x, the mean, the standard deviation, the proportion, if you know any three of them, you should be able to find the fourth one.